Hello everyone, this is Dr. Hopkins with the next video talking about Le Chateliers Principle. So we've been discussing equilibrium. Le Chateliers Principle is related to equilibrium of reactions, of general reactions. So basically, once a reaction reaches equilibrium, it'll stay that way forever. Okay, that's what it means. When your battery dies, it's at equilibrium. It won't change unless you plug it in. So what happens if we change the concentration at equilibrium of the reactants or the products? So at that point, if we added additional products or added additional reactants, we won't have our K ratio. So the equilibrium ratio will be disturbed, and we'll have what we would characterize as Q, or the reaction quotient, which we talked about in a couple of videos ago. So now what's the reaction going to do? It's going to adjust the reactants or products, the ratio of them, until it gets back to K. This is, in principle, the Le Chateliers principle. So basically, if you have something in equilibrium, if you perturb it, it's going to go back to equilibrium. So it'll either use up reactants or products or so forth. All right. So Le Chateliers principle is kind of a cheap way to get your name on a principle, because basically all you're doing is saying, hey, yeah, I realized that delta G will tell us that thermodynamics is going to go to where it's supposed to go, and so I identified it and put my name on there. So this is just what we've been talking about all along, which is that free energy and thermodynamics dictate the final reaction or reactants and products in reactions. Okay. So practically, what does it mean? So let's look at, say, a general. Let's just make it as easy an equilibrium as possible. A going to B, back and forth. So Le Chateliers principle, if we add additional A, let's let that go to equilibrium. Let's add some more A. It's going to shift and make more B. So it's going to shift to the right. If we add more product, B, it will shift back towards reactants. So it will shift to the left. If we react away, or if we take away some A, and typically the way you take a reactant or product away is by having another reaction that takes it away. So we react away A, the reaction will shift. It will change some B back into A, so it will shift back towards reactants. If we react away our product, all right, so if for some reason we remove it from our equilibrium, the reaction will shift to make more of B. So what happens if we increase temperature? Well, at this point, let's look at this. So the temperature dependence of equilibria. So basically, if we increase temperature, it depends on whether the reaction is exothermic or endothermic, what's going to happen. So we're going to take our endothermic and exothermic. That's when we're talking about delta H less than 0 for exothermic, delta H greater than 0 for endothermic products, which you learned processes, which you learned last semester. And we're going to define the heat that you either get out or put in as a reactant or product and apply the same Le Chateliers principle. So we've got our A and B. Now I have a delta, which represents our heat. So in this case, it's an endothermic. We must add heat to make it work. And then in the case of exothermic, you get heat out. So heat is now a product, whereas in endothermic, heat was a reactant. So if we treat temperature as heat, which is close enough, for an endothermic process, if we increase temperature, it's like we're adding a reactant. We're going to generate more product, so it will result in more B. If we increase temperature for an exothermic process, it's like adding a product, and we're going to push the equilibrium back towards A. So we'll result in more reactants. So that's what the temperature depends. So it depends on whether we're exothermic or an endothermic process. So if we were to go back, if we were to look at any of our processes, we'd have to know the delta H of reaction of that particular reaction. All right, so let's apply this principle to an actual reaction, not just a general A to B. And so we'll use the one we used in the last slide where we were doing some equilibrium calculations with hypochlorous acid. And we added it to water, gives us H3O plus and ClO minus. Let's let that come to equilibrium. So what happens if we were to add more HClO? So add more of our acid. Well, we're going to generate more products. We're going to end up with more H3O plus, and ClO minus. So what if we add sodium hypochlorite? Okay, now sodium hypochlorite is going to dissociate into sodium plus and ClO minus when we put it in water. So that's the same thing as adding the product ClO minus. So if we add product, we get more reactant. So we're going to get more HClO. What happens if we add water? It's a reactant. So if we added water, we add a reactant, should we get more H3O plus and ClO minus? No, we won't, because water is a pure liquid and it doesn't factor into our equilibrium. So it doesn't matter how much water we add. Remember we said this when we established this idea of equilibrium or heterogeneous equilibrium. Pure solids and pure liquids don't factor into the equilibrium constant. So we can add or subtract as much as we want, and they don't matter in terms of Le Chateliers principle. So let's do some calculations. So let's calculate these equilibrium concentrations, kind of like we did in the last video, where we're going to set up this lead hydroxide solid, we're going to dump it in water, and we're going to see how much lead dissolves. So Pb2 plus, so we should get Pb2 plus and 2 OH minus. We have the equilibrium constant. What we want to know is what's the concentration of lead in water. Now we all know lead is not good. If you drink water that has lead, it's kind of poisonous. So we're going to do this calculation and then apply the Le Chateliers principle to it. All right, so we have our equilibrium set up with the lead hydroxide to solid. So what we're going to do is we're going to calculate what we would do like we did in the last video. We're going to use our ICE table, so our initial, change, and equilibrium. I'm just going to put them over there. So the solid, remember, it doesn't matter because it's not affected in the equilibrium. It's heterogeneous. So we're going to start out with, we're just going to dump some solid in, but we have initially 0 lead 2 plus, 0 to OH minus. So our change, here's where we add our algebra. So we're going to get plus x. And here we're going to get plus 2x because we have the stoichiometric coefficient of 2 here. And so then our equilibrium concentrations are x and 2x. And so we were to go solve this. So K is equal to, so it's products over reactants. There are no reactants that factor into the equilibrium. So we would write lead 2 plus and OH minus, and that's to the second power. So that is equal to x, and that's 2x squared equals 1.42 times 10 to the minus 20. So it's a very small equilibrium constant, which is good. We don't really want a lot of lead in our water. And so that would mean that this is equal to 4x cubed, because this is 4x, so this squared, this whole thing, that's 4x squared. 4x cubed is equal to 1.42 times 10 to the minus 20. And we solve for x, which is a pretty simple process. And you get 1.53 times 10 to the minus 7. And that would be molar, and that is our lead 2 plus concentration. So that's our number. Now we're going to try this using Le Chateliers principle. Okay, now let's try this where we have our lead hydroxide. So we have our equilibrium, we have an equilibrium constant. Now we're going to say, let's, instead of starting with just solid, let's throw in some hydroxide. So we're going to throw in 0.01 molar OH minus, or sodium hydroxide. All right? So let's plug this in. Now let's do our ICE table. So what we would do is we treat this as a completely new equilibrium. So these don't count because it's solid, so it doesn't really matter how much we've added. And then our initial, we're going to still say 0. And here we're going to say 0.01. So we're starting with some OH. We still get plus x. This is still plus 2x like the last time because of the stoichiometric coefficients. And we're left with x and 0.01 plus 2x. So then we set up our equilibrium, and it would be lead 2 plus OH minus to the second power. I'm not going to write that part out. I'm just going to do this. So it's 0.01 plus 2x squared equals, what was our equilibrium constant? It's 1.42 times 10 to the minus 20. Okay. Now, in this case, now remember our x the last time was 10 to the minus 7. It is unlikely that x is going to be large compared to 0.2. So we're going to make an assumption. We're going to assume that 2x is much smaller than 0.01. Now we will check this assumption at the end. So if it's not true, we're going to have to go back and square that whole thing and multiply it out. So if we do that, then that simplifies this to x times 0.01 equals 1.42, sorry, 0.01 squared, 1.42 times 10 to the minus 20. Okay, so that's our equilibrium. Here we have, now we solve for x, and x is just going to be 1.42 times 10 to the minus 16 molar. That would also be our lead 2 plus concentration. Right now, last time we got on the order of times 10 to the minus 7. Notice we now have 10 to the minus 16. What did we add? We added product, and we pushed the equilibrium back towards reactants. Okay, even though it doesn't matter that these are not part of the equilibrium, it still goes back towards reactants. We add more hydroxide, we tie more of that lead up into lead hydroxide, and we make more solid. Okay, so we reduced the concentration of lead in this by 9 orders of magnitude using Le Chatelier's principle. And we're left with our key takeaways from this video. Is that basically Le Chatelier's principle is just a restatement of equilibrium. It tells us that equilibrium will always readjust to any particular perturbation, and they will reestablish that equilibrium of K, and mostly because the free energy tells the reaction that's where it should go. But we showed in the example that we can actually use the Chateliers principle to control our reaction. So we could increase the yield of a product using Le Chateliers principle, or in our example we showed, we can reduce the lead concentration, the dangerous lead concentration in water. So until next time.